In this lecture, we are going to focus on the topics of how does logistic regression work and how to interpret the results from logistic regression. Logistic regression is one of the most popular data mining techniques used today for a number of very obvious reasons. As mentioned in the previous lecture, this technique is an extension of the linear regression technique, which makes it easy to understand and implement. Furthermore, the regression function it produces offers great explanatory power. Therefore, it is especially popular in applications where the ability to explain the model is just as important as being able to predict the outcomes of future cases accurately. So no wonder logistic regression is one of the most widely used data mining techniques today. Instead of predicting a numeric value as in linear regression, logistic regression is used in classification problems where the outcome variables are categorical. For example, predicting whether a customer receiving an offer is going to respond or not respond, whether a loan customer is going to default or not default on the loan, or in situations where there are more than two categories. For example, whether to buy, sell, or hold an investment. Another key feature of logistic regression is its ability to optimize the complexity of the model through the variable selection process, as in linear regression. This makes logistic regression suitable for big data problems where there are many potential predictor variables. The variable selection process helps avoid overfitting the data in logistic regression models. There are generally two types of applications for logistic regression: classification and profiling. Most of the applications belong to the classification category, where we use the model to predict the probability of a case belonging to a class. As with many other classification techniques, the logistic regression model would generate a probability of the case belonging to the target class. And then you compare the probability to a predefined cutoff value to determine whether the case belongs to the target class or not. By default, the cutoff value used for a binary class situation is 0.5. But the analyst can adjust the cutoff values up or down based on the actual class distribution in the data or other factors. The less common application of logistic regression belong to the profiling category. In this category, logistic regression models are used to identify the key differences between categories. For example, if the goal is to identify the key differences between companies in the tech industry and the companies in the financial industry, one can develop a logistic regression model that incorporates the various key metrics of companies and uses whether the company is a technology company or financial company as the target variable. The predictor variables included in the final model would be the differentiating factors that separate these two types of companies. So that's how logistic regression is used in profiling. To better understand how logistic regression works, we should start by exploring the differences between the two cousins, linear regression and the logistic regression. This is a simplified version of the linear regression model with intercept beta 0 and the two predictor variables x1 and x2, and the beta 1 and the beta 2 are the coefficients which show the magnitude and the direction of the relationship between the predictors and the target. Y is the outcome variable for the linear regression model, and it is a numeric value. Okay. The reason why we have y hat here is because the model is going to predict a predicted value for y. The value of y is generally unbounded, meaning that it can range from negative infinity to positive infinity. The performance measures we use for linear regression model has also been discussed in the previous lecture. The key performance measure is the sum of squared error, which is computed by summing up all the squared differences between the actual y and the predicted y, or y hat, by taking the square root of the sum of squared error. It gives us the root mean squared error, which is a popular measure to approximate the average prediction error. So those are the key features of linear regression. So what are the key features of logistic regression, and how are they different from those of linear regression? Well, let's look at those in the next slide. First, as a close relative of linear regression, logistic regression would produce a regression model that's very similar to the one that we see in linear regression. The function has the target variable y, or y hat, and the two predictor variables x1 and x2, as we saw before. In linear regression, the model provides a direct prediction of the value of the target variable, which is y hat. However, in logistic regression, a direct prediction is not possible. So why is that? Well, recall that logistic regression is used for classification problems, where the outcome is categorical. And it does that by providing the probability of a case belonging to the target class. A probability value is bounded and ranges between 0 and 1, with 0 being no chance at all and 1 being 100% positive. So as we discussed in the last slide, the value produced from the regression model is generally unbounded and ranges from negative infinity to positive infinity. Well, that creates a problem because we cannot guarantee that our regression model will produce a value for y that lands between 0 and 1. So in order to solve this problem, a series of data transformations must be conducted in order to convert the probability value that are bounded to unbounded values that can be produced by the regression function. In other words, the target variable y here is not a direct prediction of probability value, but a transformed version of the probability value that is unbounded. And we will get into the details of the transformation in a minute here. Because of the transformation described earlier, the interpretation of the logistic regression model is also going to be different from that of the linear regression model. The coefficients beta 1 and beta 2 here are not going to be the direct interpretation of the magnitude and direction of the relationships between the axis and the y. Instead, they are also transformed versions of the magnitude and directions. So in order to understand the logistic regression, you need to understand the transformation that is needed to convert probability values into unbounded values, and then how to interpret the coefficients in the function, both of which will be discussed in detail in the next few slides. Another key difference that is beyond the scope of this class is that linear regression uses the ordinary least square method to derive the regression function, while logistic regression uses the maximum likelihood method. However, the actual algorithm is beyond the scope of this course and will likely be discussed in an econometric class. So simply knowing that there is a difference in terms of the method used to derive the functions is sufficient for the purpose of this course. Finally, performance measures are different between linear and the logistic regression. The differences actually have less to do with the differences between the two types of regression, but more with the difference between prediction and classification. As logistic regression is a classification technique, we would measure the model performance based on how frequently it produces accurate classification. Therefore, the preferred performance measures are going to be accuracy rate, misclassification rate, sensitivity, specificity, and etc. And all of these can be derived from the confusion matrix. In addition, performance can also be measured using graphic charts such as the cumulative lift chart, decile-wise lift chart, and the ROC curve. If you're not familiar with these performance measures yet, don't worry about them. We will discuss them in detail later. Now let's focus on the transformations that made the logistic regression work. Recall that a regression model produces results that are not bounded, but probability values are between 0 and 1. So how can we reconcile that difference and convert bounded probability values into unbounded values so that we can use the regression function? Well, the process takes 2 steps to complete. Well, first, let me ask you a question. Has anyone ever bet on a horse race or a sporting event? You are probably familiar of the term odds. Odds is simply another way to refer to probability. The definition of odds is that it is a measure of the likelihood of a particular outcome, and it is computed as the number of events that produce the outcome to the number of events that don't. For example, if you have a 6-sided die, what is the odds of rolling a 3? Well, since each of the numbers from 1 to 6 has equal chance in a die, statistically, if you roll the die 6 times, each number would appear once. One of these times, you are going to roll a 3, and 5 of these times, you will roll a number other than 3. So the odds of rolling a 3 would be 1 to 5, or in a different form, 1 over 5, or 0.2. Another more popular way of computing odds is using the ratio of the probability of an event happening and the probability of an event not happening. So let's say the probability of event happening is P. Well, then the probability of an event not happening is obviously 1 minus P. For example, the probability of rolling a 3 using a 6-sided die is 1 over 6. And the probability of not rolling a 3 is 1 minus 1 over 6, which is 5 over 6. and the ratio between these two numbers would be 1/5 or 0.2 as well. Well, let's look at another example. If a horse has an 80% probability of winning the race, then the horse has a 1 minus 80% probability of losing the race. The odds of the horse winning the race would be 80% divided by 20%, or equal to 4, suggesting a relatively high likelihood of winning the race. Conversely, if a horse has only a 20% probability of winning the race, then the probability of losing the race is 1 minus 20%, or 80%. And that will give you the odds of 1/4 or 0.25, suggesting a relatively low likelihood of winning. And similarly, we can convert odds back to probability easily using another formula on this slide. Probability equals to odds divided by 1 plus odds. For example, a horse that has the odds of 4 to win the race would have the probability of 4 divided by 1 plus 4, which is 80%. Well, let me give you another example here. The odds of winning the grand prize of Powerball is 1 to 292 million and 201,338. So in other words, the odds of not winning the grand prize of Powerball is 292 million and 201,338. So the probability of not winning the Powerball would be 292,201,338 divided by 1 plus 292,201,338. Because compared to the odds, the number 1 here is so small that we can almost ignore it in the equation. And that shows the probability of not winning the grand prize of Powerball is pretty much 1 or 100%, which is probably consistent with our actual experience. Well, why do we talk about odds here? Well, because it's an important piece of the puzzle in the transformation in logistic regression. Now that we understand where odds came from and how to convert between probability and odds, we can talk about the properties of odds. First, odds can be any positive number. A small odds means low likelihood, whereas a large value for odds means high likelihood. But the value of odds will never dip below 0 because the lowest likelihood is 0 or not happening at all. For example, if the probability is 0, then the odds is 0 divided by 1 minus 0, and that equals to 0. And that is the lowest value for odds because there is no probability that is lower than 0. For a relatively small probability, like 0.1, the odds equals to 0.1 divided by 1 minus 0.1, or 0.9. and that equals to 0.11. And for a very high probability of 1, the odds is 1 divided by 1 minus 1, which is 1 over 0. And that is undefined because the denominator cannot be 0. But practically, as the probability gets closer to 1, the odds value will approach infinity, which is a very, very large number. As these examples show, odds value can range from 0 to positive infinity. And if you plot the odds values against their corresponding probability values, you will also find that odds values are not symmetric. You will find that when the probability value is at the middle, or 50%, the odds value is exactly 1. The chart on this slide shows the relationship between odds and the probability. One thing you will notice is that both odds and the probability tend to move in the same direction. The greater the probability, the greater the odds, and vice versa. But neither probability nor odds will be less than 0. Okay, as you can see here, if we convert probability values into odds, we are stretching the value from a range that's between 0 and 1 to a range that's between 0 and a positive infinity. Well, that only does half of the job, because our goal is to convert probabilities to a value that can range from negative infinity to positive infinity. And by converting probability to odds, we have only accomplished half of our goal. So, what about the other half? To solve the other half of the problem is relatively simple. All we need to do is to perform logarithm on the value of odds. More precisely, converting odds into log odds. The natural log uses the mathematical constant e as the base, and it is often written as ln. And you can find the natural log of a value in Excel using the formula equal to log, and then between the parentheses you will provide the value. For example, the natural log of an odds value of 0.1 would equal to negative 2.30, and the natural log of an odds value of 1 would be 0, and the natural log of an odds value of 10 would be positive 2.30. Now let's examine the properties of log odds. This diagram plots odds and the log odds against all possible probability values. The blue curve shows the odds, whereas the red curve shows the log odds. One thing you will notice is that log odds is symmetric. The values range from negative infinity to positive infinity. And the dividing point is where log odds equal to 0. which is also the midpoint for probability, 50%. The other property is that probability, odds, and the log odds all move in the same direction. The higher the probability, the higher the odds, and the higher the log odds value, and vice versa. When the probability is high, the odds value would be a large positive number, and the log odds will also be a large positive number. When the probability is low or lower than 50%, the odds is going to be a number that's between 0 and 1, and the log odds will be a negative number. Now we have completed our transformation. By transforming probability into odds and then log odds, we have stretched the range of values from 0 to 1 to negative infinity to positive infinity. We are now ready to use the regression function to predict probabilities. There is actually a name for log odds, and that is called the Logit. So essentially, the logistic regression model produces the Logit score, which is log odds, or we can write it as log probability divided by 1 minus probability, as it is written here in the equation. So as you can see, although the function does not directly predict probability, we can actually convert the Logit score back to probability by reversing the transformations discussed before. For example, if we get a Logit score of 5 from the function, we can first convert it to odds by using the exponential function, or the exp function in Excel. The exp function, or the exponential function, raises the mathematical constant e, which is about 2.71, to the Logit score's power. In this case, 5th power. And that gives us the odds value of 148.41. We can then convert odds to probability using odds divided by 1 plus odds, which gives us the probability value of 0.9933 in this case. There is a more direct way to do this, that is to use the logistic response function. Mathematically, the logistic response function and the process I just described are the same. Using the function, you can compute probability directly as 1 divided by 1 plus e raised to the power of negative Logit score. For example, if Logit is 5 again, we can compute the probability as 1 divided by 1 plus e raised to the power of negative 5. If you do the calculation, this is 1 divided by 1 plus 0.9933 0.0067, and that will give you exactly 0.9933 as well for probability. Since this is a more direct way of computing probability and can be easily automated in a computer program, the logistic response function is the more common method, but either approach would give you the same answer. So this is essentially how to interpret the prediction results from a logistic regression model.